And at the outset, I extend a warm welcome to all the participants. And it is really an extreme pleasure on my part to meet you, my counterparts, my colleagues who do the same profession and same practice at different other colleges and university, which I do at IIT Kharagpur, and also love the same subject which I do love and teach. This is really a great opportunity and great pleasure. First, let me express this pleasure which I did not have earlier because I did not face such situations earlier. So with this, I will start the teaching of fluid mechanics, and in continuation of an excellent talk by Professor Sundararajan, T. Sundararajan, who is an well-known exponent in the field of thermofluids. Really, in continuation of that, I now first like to tell you the importance of the subject fluid mechanics. Now, this definitely comes in our mind first, that to learn a subject, why do you learn? What is the motivation behind it? Professor Sundararajan already told many things, perplexing questions in fluid mechanics, different paradox, how it can be explained. It can be explained only through fluid mechanics principles. But I let you a very short story, not in the sense that the characteristic feature of the short story is a stun at the last, but it is by literal sense, a story which is very short. The story is like that: a very smart, intelligent boy, very smart, intelligent and inquisitive boy used to live with his parents in a metropolis, in India for example. Then what happened? He was exposed to different kinds of things happening outside, surrounding him, through TV, media, through his knowledge gathered by his visit with his parents to different places of interest, and also through the instructions at his school. And the boy was so smart and at the same time inquisitive. He had several questions he used to ask his father regularly. Because you know the child psychology is that at up to certain age they feel that all the questions they have in mind, probably father is the person who can answer all. Incidentally, his father was an expert in commerce. But he used to ask the questions to his father. I could collect some of those questions. Let me read out first those questions asked by that small boy. How do we breathe? This starts from our daily life to all the happenings which he could conceive through all this media. How do we breathe? How do we feel comfortable when fan is on or we are in an AC environment? How does cold wave come in winter to make the season cold? How does the depression as termed in weather forecast take place, being associated with rain and storm and its subsequent movement from one location to other location? How is cloud formed? How does a bird fly? How does an insect fly? How does an aircraft fly? How does a rocket go up and leave the Earth's orbit? How does a ship float? How does a submarine go or move? The recent disasters of that submarine. Then how does tsunami come and how to mitigate it? Why the shape of the body of a racing car is different from that of our car? What limits the height of the tidal wave under normal conditions? How does our heart work? How trees take food from the ground and grow? How does a cricket ball swing? Nowadays cricket is very favorite, and a outswinger, very good batsman, is out, caught at the slip. So how does a cricket ball swing? How do the turbines producing power, gas turbines, steam turbines, hydraulic turbines, give mechanical power which is converted to electrical power? So all these questions actually was asked to his father, and his father, being a man of commerce, he was feeling little uncomfortable, and he told his son one day, look, I am not a person of science or engineering, so I cannot answer these questions, and moreover I feel that a single man cannot answer your questions. We have to go to a aerospace engineer, we have to go to a mechanical engineer, we have to go to a physicist, we have to go to a botanist, we have to go to a doctor, like that. But incidentally, the person has a close friend who was a person of thermofluids. He is an expert in the field of thermofluids, and one day he visited his house and told this thing. Then his friend told, yes, I understand your problem. It is very difficult for you to answer this question. This is because so many varieties of question. You are correct, this have to be answered by several persons. who are experts in the respective domain, and at the same time, you being a man of commerce, you cannot answer. I also cannot answer many questions asked from the commerce since I am not in the field of commerce. But after a while, he told with a smile that incidentally, if we could have know the fluid mechanics and its basic principles, you could satisfy your son to a large extent by answering almost all the questions. So then and there, this man determined that he will motivate his students from then onwards to pursue the course on fluid mechanics or to grow up so that he takes this fluid mechanics as a specialization. So this is the importance of fluid mechanics, that all these questions that I told can be explained by the principles of fluid mechanics. So we see that in each and every activity of our daily life, everything which is happening in nature, everything taking place in different industrial sectors, whether it is a power industries, whether it is a process industries, whether it is heavy industries, whether it is agricultural sector, fluid mechanics in some way or other is very much involved in it. So therefore, we understand the importance of fluid mechanics, and we should be proud and happy that we are in this field and we are teaching the students the principles of fluid mechanics. So very fast I will come to tell you the first part of this fluid mechanics course is the difference between solid and fluid. These always come at the very first topic of teaching of fluid mechanics, and I hope that all of you do so. Now, as we know that the matter in nature usually exists in three phases: solid, liquid and gases. And very simply, we define fluids that comprise gas, liquids and gas. So liquid and gas comprises fluid, and there are differences between solid and fluid from different point of view, from molecular point of view, as far as the molecular interactions, the cohesive force between the molecules. But from the mechanics point of view, we have to find out what is the difference between solid and fluid. Fluid comprises liquid and gas. And colloquially, we can think that fluid is a substance that can flow. That means liquid gas, as our common experience, is capable of flowing, but solid usually doesn't flow. So with this view, that from the viewpoint of mechanics, we make the difference between solid and fluid. Now, let me tell you first, before showing you anything in figure, that the basic difference between the solid and fluid lies that a solid has a preferred shape to which it relaxes when the external forces are withdrawn from it. And solid can resist the external force under static equilibrium after a finite deformation. Now you see, this is like this. If there is a solid element like this, A, B, C, D, and if we apply a shear force like that, F, then what happens is that after a finite deformation, the solid resists this force under static equilibrium. Let alpha is the deformation angle. And if this force is withdrawn, if the solid is a perfectly elastic solid, it relaxes to its original shape A, B, C, D. This is the basic characteristics of a perfectly elastic solid. Now, on the other hand, what happens that fluid, whether liquid or gas, does not have such preferred shape to which it relaxes if the force is withdrawn. And what happens when the force acts on it, it cannot resist the force under static equilibrium with a finite deformation. Rather, it goes continuously deforming. That means if I compare this by identifying a similar fluid element of fluid A, B, C, D between two plates, upper and lower, and if a force is acting like this which causes a tangential force on this. Now here one thing, solid and fluid, solid can support both tensile and compressive normal stresses or forces, whereas fluid cannot support tensile force or tensile stress, it supports only the normal compressive forces which are known as pressure. Afterwards we will see that when fluid is at rest, the pressure becomes the hydrostatic pressure, otherwise it is hydrodynamic pressure or mechanical pressure, that we will come afterwards. But now let us have this distinction with respect to a tangential force, shear stress, which can be supported both fluid and solid. So this is the solids configuration, now this is the fluid. Now if we exert a force to make this plate moving, what happens with this fluid element? There is a tangential force acting which acts as the shear force. It is a similar situation to that of the solid. But what happens here, the fluid element ABCD continuously deforming like this. Let it continuously deforming like this. It is C dash, D dash, it is C double dash, D double dash. That means with time ABCD becomes ABC dash D dash and ABC double dash D double dash. So a fluid element continuously deforms under the action of this tangential force, unlike the solid. Here 2 points are very important. Number one, that when this force is withdrawn, the fluid does not come back to its original shape. Okay. Number two is that since this stress here, for example, this tangential stress or shear stress causes a finite deformation, so stress is expected to be a function of the deformation. Here angular deformation, that we will come afterwards. Since there is a continuous deformation, this continuous deformation with time constitutes the flow of fluid. Fluid cannot resist this under static equilibrium. It resists under dynamic equilibrium. That means a continuous deformation takes place. So stress, here the tangential stress becomes a function of deformation rate, because when something changes continuously, we bring the rate. It is the rate of that change which comes into picture. The relationship between stress and deformation is known as constitutive equation of any matter. So the constitutive equation for solid is stress as a function of deformation, which is known as strain. It may be linear, it may be angular deformation, whereas constitutive equation for fluid is stress as a function of deformation rate, because it has a continuous deformation. Now in this respect, another very important thing, as I told earlier, that this comes to its original position where this doesn't come to its original position. First one. Then third one is that, which is very, very important, that this happens, the continuous movement or continuous change of deformation with any infinite small amount of force. With any infinite small amount of force, whatever small it may be. It is very, very important. Why? I tell you that if that means that any infinite small amount of force or tangential stress, the deformation will take place continuously. That means like this, that if you make a plane where the ordinate is stress and this one is the deformation rate, it may be, for our understanding, tangential stress or shear stress, and this is angular deformation rate. I simply write deformation rate. This meaning of however small means that the constitutive equation will start from the origin. That means it may be linear, it may be non-linear, but it will start from the origin. That means whenever there is a stress, infinite small stress, there will be a deformation rate. And this type of fluid is known as pure viscous fluid, which starts deforming even with infinite small amount of tangential stress and which does not regain its original shape when this stress is removed. Why this is very important? Solid also we know that after certain limit of this force, the solid also moves, it reaches the plastic region. Beyond the yield point, yield stress, a solid, there is a movement of the solid, continuous movement with time, and that is known as the plastic region. So when this plastic state, the solid reaches the plastic state, or there are certain substance which behaves like this plastic flow, that after a yield stress, this is the yield stress, if I represent stress, this tangential or shear stress at tau, yield stress, there may be movement, that may be the startup, that may be linear or non-linear, and this is known as plastic. But the behavior of the flow in the plastic region or the plastic flow and the pure viscous flow is different, but the continuous flow starts. For an example, paste, paint, peach, jelly, some biological substances, polymer solutions, they behave like that, that they do not flow with an infinite small amount of stress, tangential stress applied to them. So some yield stress, beyond some yield stress they flow, and they are plastic flow. And this is not a pure solid and pure liquid, pure viscous liquid. This is a very hazy picture. It is a mixture of both these two. They behave both as a elastic solid and a pure viscous solid. And that's why sometimes it is told that a elastic solid, since it completely relaxes to its original shape after withdrawal of the force, this elastic solid is told as the substance with perfect memory. And since the pure viscous fluid does not regain its original shape, it is known as zero memory, and plastic state of substance which flow like this is known as partial memory substances. So this constitutes the basic difference between solid and fluid from the mechanics point of view, that stress is related to the rate of deformation because there is a continuous deformation, and if we withdraw this stress, the fluid element cannot regain its original shape. Now with this I end this discussion on distinction between solid and fluid. Now I will come to next topic, which is there, as you know, continuum. Now for continuum, I don't think there is much to write, rather to say what is the continuum. I think all of you know the continuum. The matter, any matter is a fluid, solid, as we know, is composed of innumerable molecules which are moving, which are in state of motion in a random way with different magnitudes, moving in random directions and colliding randomly with each other. So therefore fundamentally it is obvious, this is the gut feel, that definitely to analyze any property or to analyze the motion or to study the mechanics, it is definite that we have to study the behavior of the each and every individual molecule, because each matter has innumerable molecules. So therefore their motion and their other behaviors have to be studied. But it is impossible task. Just you see that how can you consider all the individual molecules. If you think of Avogadro's hypothesis, you know that 1 mole of a gas, if you think of a gas, because gas contains less number of molecules than the liquids for a given volume, even 1 mole of gas, ideal gas, at normal temperature, at normal condition, temperature and pressure, contains 6 point something like 03 or something into 10 to the power 23. So 6 into 10 to the power 23 molecules. So now, for example, if we study mechanics, fluid mechanics. If you write the equation of motions, they have to be ascribed with velocities. And if we consider a reference frame, three axes mutually perpendicular to each other, then we have to ascribe three translational velocities, three rotational velocities, and corresponding equation of motions for each of the molecule will be having 6 equations. So 6 into something 6, 10 to the power 23. So many equations we have to solve. It is impossible. So this cannot be done. This is a formidable task, and this is known as individual molecular approach. Individual molecular approach. Now, what is the clue? You see, when God gives us the problem, the beauty is that God gives us the clue. But sometimes we are so, what I will call, not so knowledgeable or so ignorant to do not find the clue. Brilliant people find the clue from the nature. So God tells that I have given you the problem, I have also given you the clue, but I will not tell what is the clue. You have to find it out. Great scientists can find it out and we cannot. That is the difference. So clue is there that this randomness of innumerable number of molecules can be defined by statistical average. So that instead of unnecessarily as a madman searching for all the molecules, the description can be made by a statistical average property of the molecules. So statistical average property of the molecules, that can be, so the molecular randomness is such that we can define a statistical average. And therefore a statistical average behavior of the molecules can be made, and by which we take a number of molecules and their statistical average is expressed, and that is the study of microscopic approach. Microscopic approach, which is followed in kinetic theory of gas. Kinetic theory, not gas, kinetic theory of matter, statistical mechanics, this you know, mechanics. This comes under this type of studies, microscopic approach, which is this statistical mechanics, kinetic theory of matter, where the statistical average of the assemblage of molecules are being expressed. But there is another approach which is known as macroscopic approach. What is this? Macroscopic approach. Now here we do not bother. That means we bother neither of the individual molecules, even of the statistical average of the number of molecules as a group. We only bother about the influence or manifestation of the statistical average behavior of the molecules on the gross behavior of the system on a macroscopic scale. Gross behavior of the system on the macroscopic scale. For an example, pressure. Now pressure is because of the innumerable collisions, pressure exerted by a fluid on a wall. It is because of the collision, and due to the collision there is a change in momentum, and change in momentum means there is a force. So therefore there are innumerable forces, random forces by all the molecules. So individual molecular approach will find out the forces of all the molecules that are colliding in the wall. But the microscopic or statistical mechanic approach will be to study the same thing by a statistical average technique, by a number of molecules. But what macroscopic approach, the people with the macroscopic approach will look that how this can give rise to the gross effect of pressure at location, which can be defined the force divided by the area of that small location. This can either be, this will be perceived, can either be either by sense or by measurement, so that we can define the quantities or the properties like pressure, like many other properties like density, and we can make a variation of this, special variation of this in our physical picture or the physical problem. Okay, then try to understand what is the macroscopic approach then. Macroscopic approach is the gross effect of the statistical average behavior of the molecule on those properties which can be defined at a location and its variation. So therefore, if we can do that, that means we can sense that, we can measure that, and we can write the conservation equation by applying differential calculus for that particular property or parameter. That is the macroscopic approach. But to do that, what we require? We require a uniform distribution of the molecules throughout the medium, and that is known as continuum or continuous medium. Continuous medium. That means to do that, we can define the property, we can define the parameter at any location, infinite small location, and can have the change, spatial change with the minimum resolution required. But there is a danger. What is the danger? Because in fact, these are composed of molecules and there will be a void. Molecules, in between molecules there is a void. So danger is that molecule, the voidness of between the molecules are defined as molecular mean free path. That is the statistically average distance between successive collisions. So one side, this is lambda. That means our infinite small element for continuum studies or for continuous medium should not be with the order of lambda, so that we miss the information, we have the error. For an example, I am telling that if we want to find out, compute the density, we know from the fundamentals it is the manifestation of the molecules. That means we describe some small elemental volume and we count the molecules, we find out their mass and volume, and that is the density. We think this way. Now if this volume is very small, what will happen? Molecules are randomly coming and randomly going. So at any instant, number of molecules will be affected by the uncertainty of the influx and efflux of the molecules. But if that volume is such that it is much larger than the mean free path of the molecule, then the uncertainty in the number of molecules influx and efflux will not make a much change in the number of molecules in that volume, so that the error will be nil, approximately nil. So therefore, this is one side restriction, that it has to be, that means our scale, that is the geometrical scale, has to be such that it should not be that much small. You understand? Another side we see that L is the characteristic length scale or geometrical scale, or scale, geometrical scale. That means it should be such that it should contain more number of molecules, but at the same time it can capture that resolution which we require to express the spatial variation. So it is clear. That means to have a continuum approach to be valid, so what we will do, the problem which will be solved by this assumption that continuous medium or continuum should be such that lambda should be much smaller as compared to the characteristic length of the problem. Because our resolution, length resolution for explaining or describing the spatial variation of the property is dependent on this characteristics length scale or geometric scale. That means which is the physical dimension of the problem. For example, the flow takes place through a duct. It will be the hydraulic diameter of the duct. Flow takes place past a circular cylinder. It will be the diameter of the cylinder. These are the characteristic length scale of the problem. That should be sufficiently large as compared to lambda, so that we have this continuum hypothesis. That means at any point which we call there, that is nothing but an infinite small region which should be as large to have more number of molecules, so that molecular uncertainty in the calculation is not there because of the uncertainty of molecular influx and efflux, and at the same time that should be smaller enough to capture the spatial resolution or to describe the spatial variation at the macroscopic level. So therefore, there are two things based on which optimization has to be made, and because of that a non-dimensional number took the birth, that is ratio of mean free path to the characteristic length of the problem as Knudsen number. And I tell you the regime is like this: when Knudsen number is, this is Kn is less than 0.01, it is increasing this direction, this is continuum. That means 0 less than Knudsen number less than is equal to 0.01. And another side, if it is more than 10, that means Knudsen number more than 10, we have free molecular flow. In all our practical cases, usually we encounter Knudsen number is usually less than 0.01, our continuum approach is valid. There is a region up to 0.1, between 0.01 and 0.1, this regime of Knudsen number, continuum approach is valid, but with slip flow regime. I tell you the difference. It is continuum with no slip, and it is slip flow regime, that means with slip at the wall but continuum in the bulk flow. Just for your information, and this regime is known as transitional regime, which is the transitional zone or transitional regime from the slip flow with continuum in bulk flow to the free molecular flow. Now I tell you little bit of what is continuum with slip, no slip, that without slip, and is continuum with slip. I think Professor Suman Chakraborty will give you a detailed thing, but I just tell you a very brief introduction. All of you know that whenever fluid flow takes place in practice, there will be an adjacent solid, fluid flowing through internal ducts, fluid past external bodies. So in all situations, fluid will be in contact with the surface. So no slip condition, as you know, tells that the tangential velocity of fluid, that means the fluid velocity in the direction of the solid, that means along the solid, there is tangential velocity relative to the solid at the solid surface is 0. That means there is no relative tangential velocity component of the fluid at the solid surface. That means the fluid molecules, if you think at the molecular level, adhering to the surface, solid surface, is at the with the solid velocity. If the velocity of the surface is 0, it is at 0 velocity. This is the paradigm of no slip. And why this no slip condition is prevailing, I tell you, I also don't know the answer very accurately. There are many theories. Till date, people are arguing with different theories. Initially, we used to think that it is the strong adhesion between the liquid and the solid, a van der Waals attraction type of thing. So that solid surfaces always absorbs the liquid molecule, does not allow the molecule to slip over it. And some theories put forward like this, that there is a continuous adsorption and after some time desorption. So this process slows down the fluid velocity down to the solid velocity at its surface. There are many such theories. One theory, as Professor Sundararajan explained, that for a surface, the roughness is there, even for a very smooth surface, which are of micron or nano size, with small asperities, which traps the fluid in that very small projections, so that fluids are unable to move. So there are many such reasons, and all the reasons can be generalized, told in a very generalized way without knowing much, that it is the fluid solid interaction at the surface which in most of the occasions does not allow the fluid to slip. Now question comes, when Knudsen number is more than certain value, how the slip takes place? Now think in that way. Knudsen number exceeds certain value, this can happen in two ways. One way, by a increase in the value of lambda, that means the mean free path increases, which means, for example, a rarefied gas. then what happens is that when mean free path is increased, one thing I forgot to tell you, that to no slip condition to be valid, there has to be thermodynamic equilibrium at the surface. So when the mean free path is increased for a rarefied gas, then the number of collisions are reduced, and as you know, for thermodynamic equilibrium to exist at the surface, the number of collisions has to be many more. So reduction with the number of collisions, the thermodynamic equilibrium at the surface is distorted, so that it allows the fluid to slip. On the other hand, yes, I can reduce the length scale of my physical problem, the denominator L, to make the Knudsen number that value or more, 0.1, so that slip occurs. What is the physical reasoning? That means when the fluid flows, for example, through a channel of or through a duct of micrometer dimension, that is the domain of microfluidics. There what happens, high shear rate acting on the fluid particle may, this is one of the reasons, I am not telling this is the sole reason, may make a counterweighing effect over these attractive forces between, the adhesive forces between van der Waals type of attraction between the fluid and the solid. So these are the physical reasonings, but there is not a solid and unique physical, I tell you, reasoning for slip to occur. But however, this regime is the slip flow regime, means there will be slip at the wall, but we can use the continuum approach, that macroscopic approach, in the bulk of the fluid. There will be a trapping of air, there will be the formation of vapor and bubbles. There are numerous theories which are at the very advanced level which explains the slip phenomena. But at this moment we are not putting our head there. So we know that the Knudsen number regime for this thing to define the borderline of the continuum. So I think this is all from my side. Now I will hand over to Professor Suman Chakraborty, who will tell you about the viscosity, surface tension, other main properties.